Hi, Doug here. So I want to introduce you to the robot project. So this is going to be a new multi-part video series. I don't know how long this project is going to take, but I want to kind of explain to you guys what this is all about and why I took it on. So behind me here, well, the elephant in the room, we'll address first this guy. This is a COMAU robot. It's an Italian robot, so think of this like a big Ferrari, if you will. I still can't say where this robot came from, but it did come with this really cool stool that I'm not really sure what it was for, but it's pretty awesome. So this robot is an industrial robot. So that means it was used in industrial applications to be used for welding or adhesive applying, things like that. This particular robot is very efficient for its size, but the problem is it gets that efficiency by using really high voltages. So for example, this robot here uses 480 volt three-phase power, which is really not obtainable by most average people in their average environment or their average lab. Like the lab here, 240 volt split phase, which is more commonly referred to as single phase, is what we have to work with. That is not going to feed into this controller, that massive box over there, and get it going. But I'll walk you through that process. This robot here is 1,480 pounds. Getting it into the lab here was an adventure. But we got it here, and it's on these industrial rollers. These are rated for 1,700 pounds. You can rotate them. They have a caster on top, rotating plate, if you will. So allow me to move this around the shop until I find a home for it, and then I'll get bolted down to the slab here when that time comes. These giant black things here are giant servo motors. These are big three-phase permanent magnet induction motors with encoders on the backside. So if I can't get this controller to work, I'll be building my own interface for that. I can find some open standards for these encoders, and I should be able to write my own three-phase motor driver, which I've done before, to power these motors, if you will. But this particular robot is direct drive. So these motors are mounted right on the axes, and there's no balancing springs or gas struts for this particular unit. So that's why they need such high potential voltages to give you the torque you need at these things, at these locations. The motors themselves leave the motor through a single shaft and go down to a harmonic drive, which is like an oval piece of gear that oscillates to basically move the gear reduction. It's a very efficient system with zero backlash or very minimal backlash that allows you to drive these actuators. So we'll get into all that in future videos. Again, I'm just trying to give you a rundown on it. But the position it's in right now is where I drove it before we disassembled it and removed it from the company it came from. And again, I appreciate you guys respecting my wishes to not share where this came from. Again, they don't wish to have that announced. And so here on out, this will be Big Red, my robot. Going forward, this is the lab's robot. So we'll just treat it as that. But long story short, I put it in this position before it was installed because I wanted to get it as compact and as low a center of gravity as possible. So this is about almost as tight as it gets. This joint here is about as close as it gets. I just want to get it short down. The problem with that is to get it to move in any position, that controller needs to be operated because there are large brakes on the backs of these motors that lock everything into place so it can't be moved. So we'll be getting to that. But more on the robot soon when we get there. What's all this other stuff I have here in front of me? Well, again, I said I need to power it. That controller over there needs 480 volt three-phase to feed it in at about 5,000 watts. So what my plan is, I'm going to take 240 volt single phase, and for my large 50 amp plug, it's going to go to these two transformers here. These are DU2, roughly 2 kilowatt isolation transformers. I'm going to be wiring these in a auto transformer setup so I can generate 240 to 480 volt at 4 kilowatt each. And I'm going to run them in parallel. So I should be able to produce 8,000 watts at 480 volt single phase coming out of those. From that, I'll go into this large box here. This large box is full of massive run capacitors. What these are for is that combines with this motor here, which I just had recently donated. And again, I like to thank everyone that supports the lab here. Like, it's incredible. This three-phase thing was donated by one particular individual, awesome gentleman. These guys are donated by another close friend of mine, awesome guy. And this was donated by a totally different person. Again, another really awesome guy that all see the support that I need and are willing to work with me on these crazy projects. So again, it's awesome that I have such great connections that people can donate all this really cool stuff to make this lab so awesome. And you guys get to follow along and learn all this stuff while I go, which is going to be really cool. This here right here is a 5 horsepower three-phase motor. So this uses 3 phases to run, which we'll get into more detail soon. But just so you know, a standard house or lab or industrial residential location with split phase, you have 2 legs of a transformer with a neutral bonded to ground. And you have this potential between those two. So each one of those legs is 120 volts to reference to ground, but on each side, you get 240 volts. With 3-phase, it's actually 3 separate sinusoidal waveforms, all separated, I think, by like 120 degrees or something, that gives you your 3 phases. Why industrial applications use 3 phases is because if you ever notice on 120 volt motors, single phase, they need these large capacitors on them. That generates the secondary phase, if you will, to allow rotation to work in a motor. That's why they're needed. 3-phase motors don't have capacitors because the actual incoming phases for all the poles move the rotor around symmetrically around the stator and allows it to rotate smoothly. It's a very efficient system. But again, it involves a whole other set of wires and a whole other set of transformers, which is why residential settings normally don't have it. So what this motor is doing is I'm working it like a motor gen. So inside there are those capacitors that go across the two different legs of this three-phase motor. So I have single phase going into the two outer legs. And when it gets spinning, the center phase is generated. And that generated phase is what goes out. Why I have this another motor back here behind it, this is a 120 volt, 2 horsepower motor. This is like a 3600 RPM. This is like an 1800 RPM motor with a gear reduction to be able to ramp this motor up. This is called a pony motor. So this motor will be used to spin up this bigger motor because I don't have run caps that are rated for 460 volts or start caps to start this guy up. So this will spin it up to speed, which also gives me a lower starting torque, big inrush of current whenever this is starting up. Once then this gets up to speed, I'll flip a switch on that, which engages the capacitors in the single phase to this, which will now be self-sustaining. At this point, I can turn this motor off. When all of this is running, this motor coming out of here will now have three-phase 480 volts. I can now feed that into that massive controller over there to fire up the robot. That's if everything goes to plan. So this multi-part video series, we're going to be going through setting up the single-phase transformers, getting the capacitor bank wired up, getting the motor run up to make sure we can actually generate three-phase power. We're going to balance it out by adjusting the capacitance to get the voltage levels right where they need to be because that guy's very sensitive. And then from there, we're going to run it out of there into the controller, and you're going to come along with the ride for first power up to see how that thing powers up. And once it does, we're hoping, fingers crossed, this thing will move, which will be awesome. So make sure you guys stay tuned to all this. I'm going to get some beautiful B-roll here. So let's first take you over to the control cabinet. Inside the control cabinet, which will open the door here, you'll see the motor drivers inside. These are off-the-shelf motor drivers, not actually made by COMAU, but modified to work with the COMAU robotics, which means there's hardware and software available online that I can interface with those with. The only thing that is proprietary is all the way on the right side here. You'll see there is a COMAU controller. That is for safety interfacing. That is for dealing with e-stops and specific robot I/O controls. The other controllers handles the brakes, the servo drives, and everything. And what's really interesting about this motor controller is the big blue box here to the left. That takes in the 480 volt three-phase AC and directly rectifies it into about 700 volt DC. That direct current runs across a bus in the back that goes to all the servo drives. That nice, smooth, direct current is what the servo drives pull off of to generate their own three-phase AC with variable frequency and variable direction to drive the robot at the speeds it wants to operate at. So it seems silly that I'm going through all this effort to generate this high voltage AC three-phase for it to just convert it back to direct current. Yes, I could directly power the bus with direct current, but generating 700 volts DC is not trivial, especially as smoothly as it needs. So if I can do this externally and power it the way it wants to be, it's minimal modification to the cabinet. I believe that's everything inside the cabinet. Come back outside here. Now we're going to talk about the controller. This guy here, which kind of looks like my first robot controller, this is the control pad or the teach pendant for the robot. On the back here, these are safety switches. So when you squeeze lightly, the robot will operate. When you squeeze too hard, it shuts off. And if you let go, it shuts off. Those are called dead man switches because you have to squeeze it to operate it, which proves that you're alive. If for any reason you get pinched or you fall and you let go of it, robot stops. If you get pinched hard and you squeeze out of pain, it shuts off as well. There's also an e-stop on top here that allows you to kill power to the robot as well. So we're going to go through all that once we get into that. This giant cable on top here is not for powering it. These giant connectors are what actually connect to the robot. This is what sends the large three-phase power to the robot and sends the encoder signals back from the robot. So we're going to get those all hooked up as we go. This panel on top here, this guy is going to eventually be part of this cabinet here. And this is from a large three-phase laser, image engineering, with breakers on it. And it has three-phase current monitoring and voltage with selector switches on the front here. So my goal is to interface this so I can actually monitor the phase legs, the voltages, and have safety breaker protection and so forth for all the actuators. This switch here, I may actually interface for the pony motor to fire it up. So I believe that covers all aspects of this. So if you guys have any questions or want to know more about any part of this project or want to lend a hand, I'm going to be posting up schematics, parts, things I'm going to need help with as I go along. So feel free to reach out and give me some suggestions and tips and things that might help. But again, I appreciate you guys hanging along and thank you very much for watching.